Welcome back. So let me continue. So I'm really getting into the nitty-gritty, right, of these things. This is what I'm trying to do. Since you're not computer scientists, it's to really bring you into the mindset of how computer scientists manage to store these things on these numbers on a hard drive. And it's not trivial at all because there's been a lot of thinking regarding this. So to recap on what we are doing, basically the idea is that we are looking at something that is basically called fixed point decimals. It's exact values. These are numbers that can be written in base 10 with a decimal period that is fixed. That's what you give with the scale. The second parameter here gives you where you put the dot, right? So if you take numeric 3, 1, it means you have exactly 3 digits and the dot is after the first 2, right? So you have 2 digits, then the dot, and then a third digit. This is what numeric 3, 1 means. And so to answer your question on Zoom, 3.14 times 10 to the power of 3, which is a scientific notation that you asked, that is the same thing as 3,141.5 that doesn't fit in there. And the reason is, if you think, if I have 2 digits, a decimal period, and a digit, anything that is greater, that is 100 or greater, doesn't fit in there. Who agrees? Anything 100 or more doesn't fit in 2 digits before the comma. Who agrees? Right? So this is the reason why 3,100 and so on, it's too big. It's more than 100. So that you can forget about it. It doesn't fit in numeric 3, 1. Numeric 3 can store 3 digits, and then the decimal period is after that because there's no scale, so it's 0. So it's 3 digits. What can you store in 3 digits? Anything between 0 and 999. So anything 1,000 and larger, don't even think about it. It doesn't fit in there, right? So this is the logic here. And this is why you get an error here. This is larger than 1,000. This is larger than 100. So it just doesn't fit. It's that simple, right? And then I explained that if it's after the decimal period and there are too many digits, that you can round. You round, it's called rounding away from 0 if there's a tie. So 3.14 gets rounded to 3 or 3.1 here. And if you have a tie, meaning that it ends with 5, then 3.5 gets rounded to 4, minus 3.5 gets rounded to minus 4, and so on and so on. Right? Who is with me? Okay, so this is how numbers, exact numbers with the decimal period always at the same place, right? That's the scale. Okay, who thinks I'm too fast? Who thinks I'm too slow and I should accelerate? One raise hand here. Anybody else think I'm too slow? Who thinks it's the right speed? Okay, so I'm staying at that speed. You can always tell me to accelerate. It depends on the years. I mean, there are years where the students ask a lot of questions and want me to go into the tiniest little details, and other years where the interests are different and maybe they won't focus somewhere else. So I'm really adapting to you, right? It's nitty-gritty, but it's very interesting to understand the mindset of that, because in the end, this is related to how we store these things and how we put the data in the tables. All right. So now I'm coming back to your question on Zoom. You asked about, what about 3.14? You know this letter E that you have in numbers? It's the scientific notation, right? Basically means that you have 3 point blah, 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 times 10 to the power of something. That is called the floating point in the scientific notation. It means that you first specify your digits, and when you say times 10 to the power of something, you basically say where you move the decimal periods, right? So that's called the scientific notation. So here, there is nothing, the scientific notation is totally irrelevant for this because we're just looking at digits, right? But if you want the scientific notation, it's much more complex. So I'm giving you a warning. I'm sure most of you will not understand all the details of that. So I'm just going to give you the intuition of what was done. Computer scientists worked on ways to store numbers in the scientific notation. For example, imagine that you have 3 to the power of times 10 to the power of 24, like 3 followed by 24 zeros, right? If you try to store it like this, the only thing you can do is literally write the 3 and the 24 zeros, but that takes a lot of space and that looks like a waste, right? what if we could store it as literally just the 3 and then 24? Like we separately store the number of zeros. That's called floating point. And indeed, computer scientists thought about that. And the way they do that is that they basically take a number. And then what they do is that they write it in scientific notation, basically with a number that is comprised between 1 and 10. So 1 included, 10 excluded. That's called the mantissa of the scientific notation. And then they have times 10 to the power of something, right? So that's called, who already saw the scientific notation? Most of you, right? But computer scientists, they don't like base 10. So what was done is that instead they use the scientific notation, but in base 2. So they take something that is between 1 included and 2 excluded times a power of 2. And so what they do is that then they encode this part, the mantissa, and then this part separately. So what they put in there in the bits, so it all ends up as zeros and ones on the hard drive, is here they put the sign. Is it a positive or negative number? That's the sign. Here they encode in base 2 the power that you have here. So 31 is encoded as 31. And here they encode the mantissa, right? All of that here, they encode here. So this is called IEEE 754. That's the name of the standard. And I have no idea why I know that by heart, but this is the name of the standard, where you have the sign, the power of 2 that you have, and then the mantissa. What is incredible is that it sounds very complex, but every CPU, every processor, like the ones on your laptop here, they are all optimized to be able to do addition and multiplication with numbers encoded like that. Very fast. So this is very convenient, especially for physicists who might manipulate a lot of scientific notation in mathematical software. So this is a standard that is extremely widespread all over the planet and that handles numbers like this. The benefit is that unlike this fixed precision that is a bit limited in the number of, in where you put the decimal dot, if you use 32 bits, so this thing, you can limit it to 32 bits, then you basically can encode powers of 10 between -37 and 37. So you can move the decimal period like 37 there or 37 there, right? And this part here gives you 7 digits in base 10, very roughly 7 digits of precision in base 10 in there. There is another convention on 64 bits, because now you know the computer architecture uses 64 bits typically. And here you have more room. So you have more room for the exponent. So now you can do all the way to 307, -307 to 308. So now you can move the decimal comma even more, right? To the left or to the right. And now for the mantissa, so the part that is here, now you have roughly, it's because it's actually in base 2 in the encoding. So it's roughly in base 10, 15 decimal digits of precision that fit here. And in fact, it's very likely you've already used that without knowing it. Who has ever seen float and double in some programming languages? This is exactly what float and double are. Float is technically this, typically, and double is this. Double because that's double the size, right? That's why it's called double. Float and double. This is what actually happens behind the scenes in the CPU of the computer. Just a warning, in Python, I think that this is what they call float. Python just has float, and that's actually what float is. Okay, so just as a warning, that depends on the language you're using. Okay, so now that's great, because again, I told you this is float and this is double. Well, in SQL, they don't call them float, they call them real, and the doubles, they call double precision, right? But there is also a way that you're not stuck to just 32 or 64. You can also put anything you'd like in there. You can put float 3, float 7, float 40, right? You can put whatever you want. But just be aware that this is actually ignored. So even if you require float 7, PostgreSQL is just going to use the 32 bits version here, right? And if you say float 53 or float 40, it's going to be using the double precision. So really what's happening is really either this or that is going on behind the scene, right? Okay, so this is called IEEE 754, and this is where you have the floating point, the scientific notation. It's inexact, that's approximates when you start doing this kind of counting, right? You have the precision, and then strange things might happen. If you tried, for example, to divide and then remultiply, you will not find exactly the same value. Who saw that happening? Mathematical software, that's the reason. It's approximate. This is an approximation of real numbers. Okay, plus with a bonus, you have extra values in the standard for -infinity, +infinity, and none. What does none mean? Does anybody know? Yes? Not a number, exactly. It means not a number. So this is the sort of things you get if you divide by 0. So if you say 2 divided by 0, you're going to get +infinity. It's not going to throw an error. And if you say 0 divided by 0, it's going to say not a number. So this is basically just to make sure that instead of throwing an error, you just have these special values. Okay? But in databases, no, I'm not going to annoy you with that just yet, with what is written below with none equal to itself. Forget about that for now. I'm going to come back to that when we cover the group by and so on. So you just know there's +infinity, -infinity, and none that are additional values for convenience for computer scientists, right? Okay. Okay, this is for numbers, right? So fixed point and floating point, scientific notation. Then we have Booleans. Okay, that's much easier. Booleans, they are just 2 values, yes and no, and that's it. That's pretty much all I have to say about it. Now, why did I cover the slide with all these stuff here? Well, just because it's about the lexical values, right? So the actual values, it's yes and no, true and false, but these are all the lexical values. If you want to say yes, you can say T, true, Y, yes, on, one. These all are lexical values of true, as the mathematical idea of true. And these are all lexical values for the mathematical idea of false. You can say F, false, N, no, off, 0. These are all lexical values. But again, mathematically, true, false. That's Boolean logic, right? Who is with me? That was easy, right? This is the easy part, okay. Now, it's actually more complex than that because in SQL, you have a third value that is basically null or unknown. It actually supports Boolean logic if you don't know the truth value of something, right? So this is just, we'll cover it a little bit later, but just be warned that this is called 3-valued logic. It can be true, it could be false, or it can be unknown. What if you want a Boolean colon? Well, it's just Boolean. So just use Boolean in SQL and that does it, okay? Mm-hmm.
So if a table has an empty column, is it filled with not a number, or does it bring traditional?
Very good question. So this is something we'll come back to when we populate the tables. Technically, if you're missing data or you're trying to populate a table and there's no value to put, what SQL is going to put in there is called null. It's going to put a null in there. It's not going to put NaN, it's going to put null if it's missing. But I'll come back on that. That I haven't covered yet. I'll explain that once we populate the table, and I'll show you what happens if you don't specify all the values. Okay. So null can have many different meanings. It can be you don't know the value. It can be you're not authorized to see the value. It can be there's no value at all. So yeah, that's kind of a joker for whenever you want something special. Okay. Yeah. So I'll come back to that a bit later. Okay. So Boolean. Okay, let's move on to dates and times. This is something that software developers sometimes forget, but in fact, if you're a company, you know how important they are in the system. So we can also store dates and times in relational tables, in columns. So let's cover them. So the dates, depending on the system, you can actually have plenty of different calendars, right? The Gregorian calendar is the one that we use right now. So it's kind of a mixture of solar and lunar. It's solar because a year corresponds to a revolution around the sun, but it's a bit lunar because the months roughly corresponds to motions of the moon. But as you notice, the full moon kind of offsets itself every month. So it's not exactly that. But basically, that's the Gregorian calendar. You need the year, you need the month, and you need the day. That's all you need. The year can also be negative, right? So by the way, there's no year 0. Many people don't realize that. It's -1 and then 1. Okay, so that's the Gregorian calendar. And then we can also have the time with the hours, the minutes, and the seconds. This is base 60. This is in base 60. So the minutes and the seconds are in base 60. It's called sexagesimal, I think, is the name for base 60. I think it's called that way. So base 60. You can go all the way to microseconds in PostgreSQL. So you can have up to 6 digits after the comma. And that's like for numeric, you can even specify how many digits you want after the comma for the seconds. Okay, and then you have what's called a timestamp, which is basically the date plus the time of the day. Now, it looks complex, but in fact, what computer scientists actually do is that they store the timestamp as the number of seconds or milliseconds that have elapsed since January 1st, 1970. What's funny is that that date is exactly the same date, roughly, as the invention of relational like data independence. So you see that's really a very important turning point in the digital history. So technically, you wouldn't actually say October 6, 2023 at 10:31 a.m. You would really store the number of milliseconds that has elapsed since the 1st of January 1970. That's what you actually store in the system. But PostgreSQL is kind enough to not throw at you that number of milliseconds, because what could you do with that? You're human, right? It will actually convert it to a date nicely displayed on the screen. And again, that brings me back to this very important distinction between the typed value and the lexical value, right? So the typed value is really the actual date that is showing to you like this. And lexically, when you use PostgreSQL, the lexical value will be year, month, day, hours, minutes, seconds. Okay, who is with me? All right. Now I'm throwing the catalog. It's like a restaurant menu, really. You're a la carte in the restaurant. You can pick what you want. So you can define the column with the type date, with the type time, and with timestamp. The number in parentheses is the number of digits after the seconds. You want milliseconds, that's 3, microseconds, that's 6. I think 6 is the maximum. And then to make it even more complex, you can say if you want a time zone or not a time zone. And this is where it starts getting very complicated when you start introducing time zones. And this is why many software developers kind of stay away from the dates because they want to avoid that complexity, but this is underestimating how important it is to the actual users who really need that to work. Okay, so with or without time zones and the date, the time, or the whole timestamp. Okay, then you have durations. Durations is like 1 day or an hour and 3 minutes, right? These are kind of durations, but be careful with durations. This is just one thing to be aware of, is that there is, you can express it in years, months, days, hours, minutes, and seconds, but be very careful about this separation here that I put as a bold line. Why did I do that? Why do you think I put that line between months and days? Yes? Yes. Exactly. You need to know which month it is because the number of days in a month varies. Can be 28, 29, 30, 31, depending on the month. So this is why I put that here. Basically, if I tell you 1 month and 3 days, and I ask you how many days is that, then you don't know. 1 month and 3 days could be 31, 32, 33, or 34 days. Depends if you're in January, February, April, or in 2003 or 2004, right? So this is why be very careful. But the rest is safe. If I tell you 2 years and 3 months, that's unambiguous. If I tell you 2 days and 3 hours and so on, then this is the safe zone. Okay. So what I put in there are all the combinations. Like this is, for example, 2 years. This is 2 years and 4 months. This is 2 days, 3 hours, and 42 minutes, and so on. These are all combinations. For whom does that make sense? Don't see any raise hand. For whom does that not make sense? For whom does that make sense? Okay, awesome. You're still here. Yeah, so this is the warning that if you start doing that, I think you're authorized to do that, but be very careful because strange things might start happening if you do that. So now that's the menu. It's called interval. So if you want to be very generic, then just say interval. The 3 here is again the digits for the seconds. 3 means you're all the way to milliseconds, milliseconds. And then if you want to be more specific, so this is what I did here. If you want to really say you want, for example, interval that's a number of years, or it's number of years and months, or it's a number of months, or it's a number of days, hours, minutes, and seconds. And here again, you can specify if you want to go here, it's to the 100th of a second, and here it's to the 10,000th of a second, right? For whom does that make sense? Pretty intuitive, right? It basically decides what kind of intervals you want to express. Okay, so now you have a huge menu, right? Let's add one more thing. You know that if you use WordPress and you try to store your blog entries inside your database, you also need to store pictures. Can you store pictures in a relational table? The answer is absolutely yes, you can store pictures. What is a picture? It's just a bunch of zeros and ones, really, right? Even a video is a bunch of zeros and ones. So you can store anything you want, technically. It's binary content. Well, the good news is that binary content is not very different from strings. A string is a sequence of characters, and binary content is a sequence of zeros and ones. So really, it's very similar. So that's the reason why this feels a bit familiar. It looks a bit like char, varchar, and text, and club. But instead of club, it's blob, because it's binary large object instead of character large object. Byte A, I have no idea if we invented that name, but byte A is what they call the blob in PostgreSQL. And then you have binary, that's the equivalent of char, except that now it's in terms of bytes. And var binary is the same as varchar, but then you think in bytes instead of thinking in characters. Who is with me? Right? Very good. So now you can store pictures in there, passport scans and so on in the table. All right. Now that was a lot of them. So let me just have a small summary of the most important ones that you can focus on remembering. So for strings, you have char, that is either only one if you don't say anything, or you specify the number of characters. Exact. Varchar is variable between 0 and the maximum of p. Club or text can be basically any length, or varchar without parameters, that's the same thing. Then in binary, you have binary, var binary, and blob. So again, look at the similarity between strings and binary content. It's very similar. Then you have numbers. Numeric with a precision and a scale. Precision is the total number of digits, and the scale is where you put the decimal periods, which again is fixed. Numeric and decimal is the same thing. This is just a synonym. You can call it either way. It doesn't matter. So numeric or decimal with a precision and a scale. Small int, and big int, you remember? Small int is on 16 bits. Integer or int is on 32 bits. And big int is for 64 bits, all the way to quintillions. Then you have the approximate. So that would be this IEEE 754 convention with the scientific notation. There's 2 of them, real double precision. So real is on 32 bits and double precision is on 64 bits. And what you find in these 32 bits or 64 bits is the sign, the mantissa, and the floating point. So the power of 2 where you put the floating points. Float P is only there to give you the illusion or the belief that you can control the length of the of that, but in fact you cannot control it because it will always fall down to real or double precision anyway. So don't really know why you would actually need float P. So you should just use real and double precision maybe to be safer. Okay, then you have Boolean, just this one, but remember 3-valued logic. Date and time. So you have date time, time with time zone, timestamp with time zone. These are maybe the most common ones. And intervals. And again, typically that's because of the wall that I told you. It's typically either year to month or day to seconds. Try to avoid intervals that cross that wall. It's at your own risk. Who is with me? So that's the menu. Now you have the restaurant menu and you're able to create the tables with all the column types that you want. You just pick them from the menu. And now this is also something that comes with experience. So typically what's going to happen is that you will have a project, you will have to store data, and you will have to think, okay, what are my columns and what are the types of my columns? And the types you just pick from the menu. You just need to pick the one that applies to what you need. And PostgreSQL will do the rest for you because it's going to ensure that this is respected. And if you break these rules, if you try to store something that doesn't fit, it's going to throw it back at you and refuse to put it in the table. So you're safe. It's going to make sure that these domains are respected. It's domain integrity. Okay, so now this is done with the restaurant menu. Any questions? Any questions on Zoom? No question on Zoom. Okay, let's get down to SQL then. Let's create and drop tables. This is the best moment where you actually get to do it. You can even do it now if you want to download the exam Docker and connect to it. If you want to have fun, you'll have exercises for that. So what can we do? We can create tables, modify tables, or drop tables on the high level. Do you remember DDL, what it means? Yes? Data definition language. This is data definition language because we work at the metadata level. We work on the table itself, the schema of the table. DML will do in 2 weeks when we actually use SQL to query tables. So DDL, create a table, modify a table. So for example, I can add a column, remove a column, and so on. Or I can drop a table. Never do that on a Friday night. You might get a phone call from your employer on Saturday, and especially in production, it's a very, very bad idea, right? Okay, so to create a table, I'll show you the SQL command that does that. What's important to understand is that when you create a table, it's going to be empty, obviously, right? You say the columns and the type, but there's going to be no data in there. I'll show you a bit later how you actually insert the data. So it's going to create an empty table, but it will have the right columns and the right types. That's called an empty extension. Extension is another name for the data in the table, so the maps. So what do you need to create a table? Well, you need to give it a name. We all like to give names to tables in databases. So we need a name for the table. We need the names of the attributes, so the headers in the columns. And then we need the associated domains because we'll have domain integrity, right? So we will associate domains to the attributes. So we'll have relational integrity because of the attributes, domain integrity because we specify the domains, and we'll get atomic integrity if we only use domains that are atomic, right? And there are domains that are not atomic. This is why I'm telling you that. And even PostgreSQL has domains that are not atomic. Okay, so let's do it. This is my hello world for creating a table. So very originally, because I told you it's structured English query language, so it's the ChatGPT of the time. So to create a table, you say create table, right? So create table, hello world table, that's whatever name you want to give to it. I'm calling it hello world table. And here you put your attributes and types. So this is the name of my attributes. I can put anything I want in there. And this is my type, text. Remember? So this one is the one I picked from the restaurant menu that I had earlier. Okay, so this is it. And it's going to create a table with how many columns? Okay, 1. And how many records? 0, because it's empty. There you go. So I'm putting on my drawings here, I'm putting the name of the table, typically, then I'm putting the name of the attribute, and then I'm putting the domain. I think the color might vary a little bit, that I think at some point I just stick to yellow for the domains. Okay, so yeah, just a comment on uppercase, lowercase, because that's often the source of confusion when you actually start using the system. So what you see in uppercase here, create tables, these are called keywords. In every language, you can have keywords, right? If, then, else, these are examples of keywords, and so on. So create tables are keywords in SQL. Why are they uppercase? Well, it's just a matter of convention, really, because if you would say create table in lowercase, that would work too, wouldn't complain. It's just that people are used somehow when they write SQL to put the keywords in uppercase. So try to have that habit as well, even though it's not required. It's going to make you make it easier to interact with other people who look at your code. Okay, so this doesn't matter for the creation of the table. Now, regarding the name of the actual name of the table, I think, and I'm speaking under the control of Xiaocheng, if you know that, I think the behavior of PostgreSQL is that if you try to put uppercase in there in the name, it's converting everything to lowercase when it actually creates the table, which can be very surprising. If you really want to have uppercase letters in the names of the tables and in the names of the attributes, you should put quotes around them. And I think it's not even any quotes. I think it's the back quotes. Is that correct? I think it's the back quotes, right? So you need to write the name of the attributes with back quotes. The back quotes are, depending on the keyboard, I think it's on the top left of your keyboard on many layouts. So if you add around Hello World table, you put the back quotes, this is going to do the trick. And somebody tells us on Zoom, double quotes should be fine as well. Yeah, this is also possible that it accepts double quotes. I'm usually scared of these things because many systems do not treat double quotes and single quotes and back quotes, so it can even change the way that this is handled. So let me tell you that if you want to be safe, just put lowercase everywhere, then you don't need to deal about these things. This is perhaps the easiest way, right? But if you ever get errors that have to do with uppercase, lowercase, and so on, it's very likely you need to add some quotes around to force a distinction between uppercase and lowercase. Would be a nice experiment to play with the back quotes and the double quotes to see if they behave in the same way. Yeah. By the way, you can do it. You can play around too. You can enter that in a Jupyter notebook and see what that does, right? All right. What if we have more than one attribute? Here you go. I have here 6 columns, 6 attributes, and you see it's always made of the name of the attribute and the domain of the attribute. The name of the attribute can be anything you want, except that if you go beyond lowercase and the underscore, so last underscore name is also commonly used, this underscore sign. As soon as it's more complex than that, you will need quotes or back quotes. And then a space, and then you pick the domain, and the domain, what is in red here, is taken from the menu. So these are all the names I gave you in the first hour, right? These varchar, char, text, date, boolean, byte A, which is this strange name for blobs. All right, who is with me? Okay, very good. And here I'm just doing lowercase everywhere, so this is why I didn't bother with putting quotes anywhere. So just don't forget the parentheses around the attribute names. And I have to give you a warning, is that now this is for PostgreSQL. PostgreSQL I picked because it's the closest to the SQL standard. It's one of the most faithful implementations. If you try to use MySQL or IBM or Oracle or Microsoft SQL Server, you might start noticing that they don't put parentheses at the same place, or there's small changes. That's again like Schweizerdeutsch that can vary from region to region. But then there's no secret. You just need to look at the documentation. But for this course, we're going to stick to PostgreSQL. So just focus on PostgreSQL, learn PostgreSQL, and later on, you just might need to adapt a little bit if there's minor differences with the system you use. But the principles are really the same. Okay, that's the schema that I get. So the name of the table is persons. I have 6 attributes here and 6 domains in here. Okay, and it's empty. Because as I say, if you create a table, there's no data yet in there. Can you create an empty table, meaning in the sense empty of no attributes at all? Surprisingly, the answer is yes, you can. So I can create a table like this that has absolutely nothing and not even an attribute. Well, I think this is more of a thing that is fun for mathematicians, you know, like a vector space with dimension 0 or that kind of things. It actually works. But in fact, you can add columns later. So you can maybe use that as a placeholder for a table that you want to create. And later on, I'd show you how you can add and remove attributes from a table. Okay, so that has no column and no extension, no data at all, no records. Okay, how do we drop a table? Well, all you need is the name, and surprisingly, it's called drop table. So you say drop table, hello world table, and that goes away. Drop table, right? So create table, drop table. All right. However, if you drop a table that doesn't exist, it's going to complain that the table doesn't exist. You're trying to drop a table that isn't anywhere in the system. Now, that's very inconvenient because this drop table, in fact, is very common when you have scripts that initialize your database. Typically, these scripts start with drop table. The first thing you do is you drop, and then you recreate the tables. The idea is that you should be able to execute it repeatedly, right? When you debug your software, you just reinitialize, and every time it drops the tables and recreates the tables. The problem is that if you already drop them and it throws an error, or the first time you execute it, the tables are not there yet, it's very annoying because that throws an error. The solution is the if exists. If you say drop table if exists, then it's not going to complain if it doesn't exist. And that's what you should have in your scripts. If you have a population script in a system. Drop table if exists, it will work the first time, and it will work the other times as well if the tables are already there. Okay, so now we can create tables and we can drop tables. What's next? Well, how do we put data in there? How do I populate my tables with data? So we'll want to insert tuples. I say tuple, I could have said map or record or row or whatever. I just use the word tuple. Update a tuple or delete a tuple. Now you saw that I changed that to DML instead of DDL. And it is true that technically, if you insert data, that's technically considered to be manipulation and not definition. So this is why we consider this to be DML already. Okay. Okay, so here how it's done. Again, it sounds like English. So insert into the name of your table. So insert into hello world table, values Einstein. So that is assuming that I created it before, right? I had a create table, hello world table name text before that I've already done. And next I say insert into hello world table values Einstein. That is inserting one record. So now I have a table with one row and I put Einstein in there. Who is with me? Okay, this is how you do it, insert into. Now you can also specify the name of the column that you want to insert into. It's kind of superfluous. I mean, it was clear there's only one anyway, but if you want, you can say into the column name, values Gödel, and now I have a second one. Okay. Now, more complex, imagine now I created that table with 6 attributes and all these types. Now I'm going to insert not one, here it was one record at a time that I'm inserting. What if I want to insert 2? Well, I just separate them with commas. So I have a first record that inserts 6 values. So there's a comma to separate each value. So this is for the first column, second column, third column, and so on, 6 values in parentheses for every record, and then a comma, and then the second record. That is again a list of 6 values in parentheses. What do I get? Well, now I have 2 records in there. Okay. Do not be scared by this. I'm not expecting you to know that to do that kind of things. This is just some syntax to insert binary contents. So this is assuming somehow we put the image in that way. Yes? Yes, that's for the type. It might be that if you don't put it, it will work as well, that it will convert it. This is called a cast or a coercion. But technically, this is basically saying that this here is meant to be a lexical value that is in fact a date. And if you specify dates, then this here will create something that has the type date. So it clarifies to the system that you're actually inserting a date, right? Now, I'm speaking very generally, right? For PostgreSQL, you should do it in that way. It really depends on the programming language. There are programming languages that are going to be very strict and that will throw an error if you do not convert it to the right type. And there's other programming languages that are very lenient. Even if you give a different type, they will try to convert it for you, right? So this is what's going on here. If you don't put date, then that's technically a string, and you would have to convert it. If you put date followed by the lexical value, then this is an actual type date. Did it answer your question? All right. Okay, and these are obviously all strings, and these are Booleans. So here I told you there's many different ways to do that, but yeah, false true are the most obvious ones. Okay, so now we have a table with two records. That starts to be interesting. Right now we are manipulating data. Yes? Yes, exactly. That's for binary values when you insert them. Yeah. The binary values, again, on the exam day, I'm not going to give you that sort of things, right? With the binary value. This is just so you know that it exists, that you can actually insert that kind of things. In fact, to give you some context, in the course, I'm making you use the Jupyter notebooks, right? So you type in the Jupyter notebooks the actual queries. In real life, when we have databases and they are behind a website like WordPress, nobody types the query directly. The query is in fact generated with Java or Python or whatever. So what's going to happen is that this AD10E7, it's going to be programmatically generated. There's going to be a computer program that takes an image like WordPress, and it's going to generate this sequence of bits and generate the SQL query for you, right? Okay? All right. But again, this date and E is to be understood in terms of you have a lexical space and you have a value space, and date basically turns it from a lexical value, from a literal, it turns it into a date, right? Okay. It's like, what is it called? Expecto patronum, right? So this is basically the magical formula to create a date or a binary value. Okay. Now, what happens if you specify the columns, but not all of them? So here I say I want to insert into first name, birth date, scientist, passport, scan, so 4 columns. What happens to the other 2? Well, this is kind of the question you asked earlier. We just put nulls in there. What I don't specify, I just put null. So null is kind of a bit special. It's put in there whenever you you don't know the value or you don't specify the value. Maybe I'm going to stop here and continue on null next week, because there's a lot of things that I could say about null, especially how it relates to relational integrity. It's very interesting to think about how this is done. Just before you go, where is it here? Of course. It's the one. Yes. So how much did you understand? I really try to finish every week with this to sense the speed. Okay, that sounds good. And even some people understood everything. This is really, really, really nice. Very nice. Most people above 80%. So don't hesitate to ask questions on the Moodle forum to us. Do the exercises. This is really practical, what I showed you today. You can really type that into the Jupyter notebook, create the tables, drop the tables. So there's nothing better than to actually do it with the Docker environment that the TA team prepared for you. Thank you very much. Thank you, Xiaocheng, for moderating, and thank you everybody for attending. Enjoy the exercise sessions, and see you next week at 10 a.m. same room. Thank you.